Hello, everyone. Thank you so much for joining today's webinar. My name is Laura Schul, and I'm the CEO of Streetlight Data. So before we get started, I want to let everybody know that this webinar is being recorded. We are going to send out a link to everyone who signed up that contains the recording and the slides about 24 hours from now. And if you have any questions during the webinar, please ask us using GoToWebinar's Q&A feature, which you should see on the panel to your right. If they're quick answers, I can answer them in writing during the presentation, and I'll also consolidate the questions and pose them as your voice to our speaker, John, at the end of the session. So with that, I'm just here to be the MC. I'd like to hand over the presentation to John Kupal from ERG, who is going to take us through some really exciting work. We have been collaborating with ERG on using data for vehicle emissions for, I think, 5 years now. And this is just the latest and I think most exciting and comprehensive piece of work that collaboration has produced. So we're delighted to have you here today. Take it away, John.
Thanks, Laura. Hi, everyone. And I want to move along here. So I'm going to be talking today at Laura's invitation about some of the work we just completed looking at telematics to model vehicle emission inventories, and it draws on, as Laura said, several years worth of different projects and work with different sponsors, so I'll be sharing that as well. And I do want to talk a bit about who I am. I've been working in the air quality vehicle emissions world for about 30 years, first with EPA at the National Vehicle Fuel Emissions Lab in Ann Arbor, Michigan, and including working extensively on the MOVES model and developing mobile source vehicle emission inventories as part of the National Emission Inventory and other regulatory processes. Spent a couple years at Nissan working on vehicle emission certification. And the last 8 years I've been at Eastern Research Group, an environmental research and consulting firm, focusing on mobile source emissions research, analysis, and modeling for clients from local governments all the way up to international clients. So just wanted to thank my colleagues and co-authors at ERG over multiple projects. Allison Den Blinker specifically has done a lot of the work that you're going to be seeing today. The Coordinating Research Council, I'll talk about their sponsorship of projects later in the presentation. The US EPA MOVES team, the CARB MFAC team, State of Colorado was really helpful on the Denver work I'll be showing, and of course Streetlight for all of their cooperation and encouragement and flexibility throughout multiple projects. So just to pay the bills, ERG is a consulting company based in Lexington, Massachusetts, of about 400 individuals, but we're all over the country. We work in all sorts of different sectors and fields. The work I'm talking about today is coming from our Mobile Sources group based in Austin, Texas. And our specific work on telematics actually started almost a decade ago. We worked with US EPA to help them look at some engine data that I'll be showing from insurance programs to start helping improve some of the vehicle activity inputs for the MOVES model. We've done multiple projects with Coordinating Research Council, which will be the focus of today. We teamed with Cambridge Systematics and UC Riverside looking at truck activity data for the National Cooperative Highway Research Program. We've done some work for California looking at heavy-duty truck mileage accrual, and we've done quite a bit of work in Mexico, including looking at congestion levels in Mexico City for the local government there as well. So this kind of broad background has led to thoughts about what's great about telematics, what could be improved in telematics to help the specific needs of vehicle emission modelers, and that's really the genesis of this presentation today. So I do want to talk a bit about the big picture air pollution in vehicles. I'll go quickly through that because many of you may already have that background. Talk a bit about the background on what are vehicle emission inventory models and their use, and then what is the activity data that we need to feed the models, and then where did it used to come from, and then where can telematics start to fill the need there and kind of greatly expand the possibilities in terms of the data inputs and the resolution of the models. And then the most recent project we did, which is the CRC, Coordinating Research Council project, looking at capabilities, limitations, and of telematics, and then finally a telematics wish list that we surveyed the regulatory agencies for, and then time for Q&A. So just big picture, Air pollution is linked to premature death and several serious illnesses, including stroke, heart disease, and cancer. So, pollution is still, vehicle air pollution worldwide is attributed to millions of deaths per year. And even in the US is, still causing problems, even though things have come quite a long way. We're seeing an improvement in air quality in the US. The number of unhealthy air days has decreased quite a bit over the past decade within the US and individual cities. But despite this, the EPA reports that there's still over 80 million people that live in areas that exceed national ambient air quality standards. And when we look at the contribution of vehicles to overall air emissions, this is coming from EPA's National Emission Inventory, we see that here we're talking, and the focus of this presentation is really, we're talking about air pollution like, ground level ozone and particulate matter, the things that have direct health impacts. A lot of what I'm talking about today can also apply to CO2 inventories, but that's kind of a different animal because the criteria pollutant emissions and the inventories that we generate for them require a lot of resolved detail in terms of vehicle activity that are important to really make sure we're putting into the models to make sure we're capturing how much NOx is coming from vehicles as an ozone precursor and a secondary particulate matter precursor, and also VOC and direct PM. And so we see when we include highway vehicles and non-road vehicles, I'm going to switch to my spotlight here. We see, non-road is kind of the other sector, that we haven't quite got to telematics for that yet, but it's, maybe not too far on the horizon. But when we look at these sources, they contribute over half of the NOx in the US, which is a primary ozone contributor. Direct PM and VOC, motor vehicles don't contribute a majority, but what's important to recognize is that this is a national total. When we look at urban areas where the air quality problems are, and of course near roads, then the contribution may be much higher. And transport is also the largest source of GHG emissions at about 20%, 28% according to EPA. So to this last point on near roads, so it's not just the total emissions, it's the idea that millions and millions of people live, work, and go to school very close to major roadways or transportation hubs like ports, and millions of school children attend school within the same distance of these pollution hotspots. And there's been multiple studies that have looked at negative health effects living near busy roads, from asthma to heart disease, including premature death as well. So we're just starting to think about, hotspot environments, environmental justice issues, sort of the negative health consequences of living very close to major pollution sources of roadways and ports and warehouses, et cetera, rail yards. Okay, a bit of background on the vehicle emission inventory models. So these are mandated in the US by the Clean Air Act. EPA must maintain and update emission vectors every 3 years and provide tools for state and local air agencies for their air quality planning. The models are used for a variety of purposes beyond these specific applications. The EPA uses them to quantify the need for new vehicle emission regulations and the benefit of those regulations. It's used for what-if analysis to look at different policy scenarios. And these models also serve as the repository of the most recent emission and activity information kind of pulled together from county level up to state level up to national level, and sort of different emission factor programs. They become the source of these data that are used for multiple applications even outside the model as well. So in the US, we have EPA puts out the official model for states outside of California, known as MOVES. And the MOVES 3 version is the most recent one, which was just released in November 2020. And the model and extensive documentation and background can be found at this website. And then the California Air Resources Board has approval from EPA to maintain their own model because of all the California specific conditions and the unique fuel and vehicle standards and activity elements, et cetera. And so they maintain the MFAC model, and the most recent version of this, MFAC 2021, was just released in January, and you can find out more information at the website shown here. Most of my discussion is about the MOVES model because that's been a focus of some of our CRC projects and of course our EPA projects. But a lot of the concepts are the same here in terms of what's going into the models and the importance of different vehicle activity parameters for characterizing vehicle emissions. So how are these models used? Again, I've already mentioned regional air quality planning for state implementation plans and transportation conformity. Those are two areas that are overseen by the Clean Air Act requirements. The national reporting function, which is where the National Emission Inventory, NEI, falls in, and that'll be a lot of the focus of what I'm talking about today. Policy evaluation, cost-benefit analysis, and then the Clean Air Act also requires transportation conformity hotspot analysis for PM and carbon monoxide to look at the specific locations and the specific emissions that are coming from changes in the transportation structure within those areas. So this chart is just showing an example application of vehicle emission models that's showing the breakdown from the 2017 National Emission Inventory, NEI, of VOC emissions by different mobile source sectors. And so models are helpful to think about how much emissions are being produced, what's the breakdown in terms of different vehicle classes. And then as I show in the next slide, another really important thing for emission modeling world and policymakers is what's the distribution of emissions by age of vehicle, for example, in this case. And this is important because vehicle emission standards now are reducing emissions at 95 or higher % lower than they were back in the 60s and 70s when they had no control. And so it's tempting to think, well, then, and of course with EVs on the horizon, it's tempting to think, well, the problem is basically over, right? And the answer is no, because the old vehicles stick around a long, long time. And as they started to have more rigorous durability requirements, now they're really starting to kind of do better in older age. And so what we see in this chart is we see, the vehicle population in the US, kind of tails off as you kind of get into older 30-year-old vehicles, but their emissions contribution of the old vehicles is still pretty significant. In fact, is still really dominant. If you look at, age 10 vehicles and older, they really dominate VOC and NOx, the main ozone and contributors, and also important contributors to secondary PM and air toxics. Most of those emissions are coming from vehicles that are older than 10 years old and even older than 20 years old. And so when we think about vehicle activity, the emission modelers in the emission world and the air quality regulators really care about older vehicles, and they care about the activity of older vehicles, and they need activity data that can address the full range of vehicle ages. This is kind of a precursor to thinking about how telematics, the gaps telematics needs to fill. Just an example in terms of how the models are used for air quality planning. So this is based on some data from like Michigan area states, LADCO is the air organization there that coordinates the state implementation plans there. And so this is an example looking at ozone monitor data from 2005. And of course, the slide's a bit dated because now we're past 2018, but at the time they were projecting forward to 2018, based on using emission inventories to look at the reduction in mass emissions and using that to project how well they will be in attainment with ambient air quality standards. And so the inputs to the model are really critical because they're really driving the policies and the need for additional controls at both the state and the federal level. And then I mentioned hotspot analysis. So again, these are required in certain areas that are in danger of not attaining particulate 1-hour particulate matter standards and carbon monoxide standards and 24-hour particulate matter standards. There's different ambient air quality standards that are looking at short-term exposure in sort of highly concentrated traffic areas. And so there's an analysis that requires using the MOVES model or the MFAC model, depending on what state you're in, looking at, what will happen if I, in this case, add a, I'm looking at the wrong screen. If you see the dot flying all over, it's because I have to train my eyes on where it's going. So for example, adding the adding this park and ride lot and adding this this terminal here, like what will that do to overall PM 2.5 concentration? Will that push this specific area into non-attainment with the 1 hour PM ambient air quality standard? And so the model, in this case, the models need very specific activity data, geofenced down to looking at vehicle volumes and vehicle speeds that are in the current condition, and then how might that change with the addition of these new elements, and what will that do to air quality? So I'm going to spend much of the rest of the presentation talking about the National Emissions Inventory, because that's been a big focus for EPA and CRC on how to make improvements to the model and the data going into the model. So the NEI is compiled every 3 years, covering all major, I showed the results earlier, major pollutants for all sectors and all US counties. 2017 is the most recent release, and you can find information on this website. And 2020 is in progress right now. 2020 is going to be a strange year, obviously, with COVID. The states, in terms of vehicle emissions, so states are given the option to either submit complete emissions, which is like, for example, what California does, or they can submit inputs to the MOVES model that reflect their local conditions, so that EPA then takes and runs to generate a national emissions inventory. States are not required to do this submission, so if they do not, EPA uses default estimates for vehicle activity and other parameters. And historically, before we started looking at telematics data, these defaults were simply a uniform national average. So you might have an average speed distribution that was applied to the entire country if states did not supply their own data. And so the idea, and some of the CRC work, was to start looking at telematics to see, even at the default level, can we start looking at county level inputs that are more accurate in terms of what's happening in the local area. And that was a big, a big step forward with telematics, as we can finally get away from a single national average because we have enough data and enough resolution to do that. So the National Emission Inventory, again, is producing emissions by county. This is an example back from 2011, but the principle still applies here. That we're, you can see the urban areas and the counties, and even with truck emissions, you can even see in some cases the highways, and kind of lightly going through the country. And so, each county, we're looking at VMT, we're looking at the distribution of trucks and cars, we're looking at the age of trucks and cars, and we're really, the backbone of this really is the activity data that we need to estimate how much emissions are coming out of cars and trucks. So we did an analysis for CRC early on when states started submitting MOVES data, looking at, well, how many states are actually submitting data. This is not any sort of political statement, but we see that the dark blue states were submitting data and the lighter blue states were not as of 2014. I think that the dark blue has expanded since then for 2017 NEI, because more and more states are submitting and seeing the value of submitting and collecting their own data. And certainly we're hoping that, as states learn more about telematics, that might become a potential source for them to think about, providing data where maybe they haven't been able to gain access to it before. And the question is, well, what are they submitting? And really what they're submitting are the things that are most important for vehicle emissions in terms of activity. They don't submit their own emission rates. That's really kind of EPA's job. But what they do have a better handle on, and this is also, I'm talking about the NEI here, but this also applies for SIPs and transportation conformity. And there is MOVES guidance that the EPA puts out on where to find the data for this. But the NEI states have a little more latitude. There isn't specific guidance for that. But they are providing data through something called the MOVES County Data Manager for county databases. So for each county in their state, ideally. They're providing, kind of the big hitters of vehicle miles traveled and the distribution of VMT by month, day, hour, vehicle populations, average speed distribution, vehicle age distribution, and other things that are important for emissions in their area, like whether there's an emission program or if there's any unique fuel properties as well. And so the question is, in terms of, and again, EPA is populating the models with default information when states are not supplying it. And so the traditional sources of vehicle activity data, whether it's through the default data or whether it's through what states are submitting include traffic counters. So, the Federal Highway Performance Monitoring System, HPMS, is kind of a national source of this, and that's implemented by state DOTs, which are kind of using that to build their own estimates of VMT and traffic flows. And this has traditionally been used to provide the vehicle miles traveled VMT and the vehicle mix to the MOVES model, at least at a default level, and generally what most states are submitting. Instrumented vehicles, so this is kind of showing two generations of data loggers. So the first one on the left here is from my colleague Tim DeFries at ERG, who was involved with, there was a seminal set of studies on instrumenting vehicles back in the early 90s called the 3-City Survey, which is still being used, and I think even in some areas of EPA and MOVES. It took these data loggers were constructed, and Tim kind of helpfully put it on a textbook so you can see how big these things were. But maybe several hundred vehicles were instrumented in Baltimore, Spokane, and Atlanta, and that kind of formed the basis of vehicle activity estimates in the mobile model before MOVES and MOVES for a long, long time until the updates started to be developed from telematics. And then more recently, there's OBD data ports. This is from HemData, the company, that plug directly into the OBD port. And so those, I know, for example, the California Household Travel Survey and other states are able to use the smaller, more portable data loggers, send them out in the mail, and then you can get a much larger sample size, but we're still talking maybe thousands. So it was, hundreds with these big data loggers, maybe thousands. So it's a much, much smaller sample size. You can't get the coverage that obviously you can get with telematics. But what it does allow you to do is it allows you to select your sample and to stratify by things like vehicle class and age. And that is important in the emissions world, and that kind of shows up again when we look at telematics wish list. Is okay, it's great we have a ton of data, but how can we make sure we're getting a range of ages, a stratified sample that we can then roll up to a representative emission number? And then finally, travel demand models, tools for regional transportation planning, traffic volumes and speeds are often rolled up to supply VMT speed distributions to MOVES also, and there's discussion in EPA's guidance about how to do that. So when we talk about telematics data, through our work, we've kind of lumped them. This is really kind of our own categorization. We think of engine data and location data, and engine data is similar to the HemData logger I just showed you, but is able to collect, not just speed and acceleration, but getting data off of the vehicle's computer, so we know exactly when the vehicle keys on and keys off. We're able to detect malfunction indicator lights, whether the vehicle is malfunctioning for emissions and how long. And so it's very detailed information. And then GPS data may or may not be included on that. So the location data is more limited depending on the engine data application. Then location data, of course, is what we're been focusing on more recently. There's just been an explosion of this because of connected vehicles and navigation devices now really just going to cell phone apps. I tend to use this interchangeably with location-based services, LBS, that Laura may correct me on that. But the important thing is, there are huge samples, and the breadth of coverage of activity is much, much greater than we're seeing with engine data. But there is no engine data, and so there's a trade-off here. Because the engine data doesn't give us very good location resolution for geofencing, and it doesn't give us the broad coverage, but it does give us things that are really important for emissions. And so we've kind of looked at both sets as we've looked at different projects. For this most recent CRC project, we looked at what was being used in MFAC and MOVES currently, and there's kind of a mix of both engine-based and location-based data. So the current models, the most recent releases, depending on the model, for example, MOVES uses some engine telematics data for trip starts, ends, and soak times, which I'll show on the next slide, and idle time. And then California we helped California look at some heavy-duty truck telematics data to look at the mileage accrual over time and the truck malfunction rate. And then the location-based data is being used for average speed distributions, in large part because of the CRC project that I'll show. and VMP temporal distributions. We think there could be a lot more done with telematics, though. On the engine side, getting information on OBD codes would be super, super helpful. And California has been looking at a lot of, for example, engine on versus engine off with plugins, and of course with EVs, we start to get into the question of state of charge. And also, now we're looking with location data. There's enough of it that we can start thinking about total VMT, which we couldn't really do before. So that's part of what we looked at with our case study. So this is an example of engine data that we helped EPA analyze based on, this was an insurance program that was using engine-based telematics. And what's sort of interesting is that, this was like 5 to 8 years ago. And when we sort of went back to the same vendor for the CRC round, they weren't able to share the same level of data now as they did 5 years ago because of privacy issues and whatnot. And so this seemed really promising at the time, but as I say at the end of the presentation, I feel like the engine sources are kind of drying up, in terms of, and this is for passenger vehicles. Heavy duty vehicles are a different animal because heavy duty vehicles are required to collect engine type data as part of electronic logging device rules that are in place in part to sort of regulate driver rest and start stop. And but my focus mostly for this presentation is light duty passenger vehicles, and I'm finding that there's just really, even for this analysis that EPA did, it would be difficult to repeat it now because we weren't able to find the same level of data. But that said, this was several thousand vehicles where they had specific key on, key off data for 5 states across the US. And what's really, in terms of the kind of the psychedelic chart here, what's really important in the emission world is that the start emissions are a huge, the emissions directly after keying on, that's what I call start emissions, are a very, very huge part of the inventory. How long a vehicle has been sitting before that key on is a very critical element to input for the model. And so having exactly when the key on happens and when the key off happens is really important for emissions, and that's something engine data could give us. And location data has to approximate this because it's just sort of, it's kind of estimating trip starts and ends based on the movement of the device itself. So this is an area where engine data, was able to kind of fill a specific need for a vehicle emissions model. And I guess, what does this mean? What it means is that, when people are starting in the morning, most of the vehicles have been sitting overnight. That's kind of what this means. And that's why you get a big slug of hydrocarbon CO emissions in the morning hours. Then of course, as you get to later times, the soak distributions kind of vary out. And there's a very sensitive inflection point to emissions when you get to about between half an hour and an hour. After about an hour of soaking, you're very close to a cold start. So whether you start after 20 minutes or you start after an hour and a half has a big difference in emissions of parking. So that's what EPA is trying to nail here. And then something else that we helped EPA with was to look at, the MIL-on, the malfunction indicators. How long are cars driving with malfunction emission systems? How long do the repairs last? And then you can start to see the trend of, people leave their check engine light on. Maybe some of you do this, but I won't judge. But so, the check engine light comes on and basically says, hey, there's an emission problem with your car. People drive several months with that, and then when it's time to get inspected, they get it fixed. So they get it fixed, they get respected, they get respected, they get inspected, they pass the test, and then it breaks again, and then it goes several more months broken. So that's why having OBD information from engine is would be really a gold mine in terms of really understanding what's happening with breaking deteriorated vehicles in use, and only engine data can give us this, not location data. But that said, there's a lot of advantages to location data that engine data don't have, and so we've spent a lot of time looking at, through the Coordinating Research Council, how to use location data primarily to improve the national emissions inventory, and some of this was carried over to MOVE's inputs also. So I'm going to talk a bit about the conclusions from these studies. The most recent one that Laura mentioned was what we call CRC E131, which is assessing capabilities and limitations of telematics data. And that is the publications pending in the Transportation Research Record. So the CRC A100 project, Streetlight worked with us to really develop a custom data draw where we were able to pull the moves speed bin information for each county in the country in sort of a summarized, aggregated way. For each county in the country, and we were able to basically populate the move speed bin inputs directly for all the counties. Most of the counties in the U.S. that we had data for. We had to do some grouping of rural counties because we didn't have enough resolution in each county. But it was a very impressive data draw. And again, this was 5 years ago, so I mean, this is earlier in terms of the sample size, so it's grown quite a bit since then. This is just kind of this is a streetlight chart, just kind of showing all of the links that we were able to represent with the data that was provided. And you can find these results on the CRC website. I showed the link earlier in the presentation, Coordinating Research Council. But for example, it showed that so we're comparing to a single average national default, which was in place before we collected this data, and we looked at 3 different urban areas, Atlanta, Chicago, Las Vegas, and the average speeds, they vary widely between them, whether it's a freeway or a non-freeway. That's what restricted, unrestricted means. And so there's pretty significant emissions implications. And Las Vegas, the average speed at rush hour is 50, Chicago is closer to 30, very different emission profiles at rush hour. And then the very big differences with the national default that would have been used without this data in place. So location data was able to provide very good speed resolution, a big improvement from the single national default. And the thing is, moves is not just looking at average speed, but it's looking at actually the distribution of individual speed bins within the hour. And what streetlight data was able to show us here was that looking at Atlanta, for heavy duty, medium duty, and light duty, there was different distributions within the same hour. And this was kind of interesting because what it told us was that there were a lot of heavy duty trucks that were avoiding the rush hour times. So most people go out on the road and they kind of take their chances during rush hour. And so during between 8 and 9 a.m., there's a lot of activity in the let's see, going for cars. Yeah, there's a lot of activity in the lower speed bins, because people are just having to deal with congestion. But the trucks were avoiding that. The heavy trucks were avoiding that, and they were able to sort of have most of their distribution in the higher part. And so we think this was showing us some sort of truck travel strategies and fleet management strategies that, really this type of data is helpful to understand, that a truck is not a car, is not a medium duty vehicle, that there are differences that can help resolve the emission inventory. The next CRC project was to look at spatial variation in trip starts within a county. So this is just an example of Cook County, Illinois. Looking at the census tract level, we were able to use streetlight data to look at the distribution of trip starts per square mile and the density of those and sort of how the travel was happening within the county. So again, previously the modeling tends to focus on county level or maybe grid cell level for air quality, but here we're able to get, to a much more detailed level of information. And this is really critical for air quality modeling, specifically to look at the formation of ozone. So I know I'm already exceeded my goal here for time. So I'm going to close out talking about the CRC E131 project, the telematics case studies. So again, there's full documentation of this on the CRC website. We ended up doing case studies in the Denver area looking at streetlight data focused on the NEI. We also had 2 other data vendors, Autonomo and Moonshadow, and we did some analyses with those. The Moonshadow, they took INRIX data and we focused on a hotspot analysis looking at emissions after an NFL game, the Denver Broncos game. So we were able to kind of geofence and drill down specifically with that. But what I'm going to focus on now is looking at the analysis we did with streetlight on comparing the NEI 2017 inputs versus what we could come up with the streetlight data. And specifically, and this happened during the first COVID shutdown, so we were able to look, streetlight was able to post data every 15 days, and so we were able to look kind of incrementally what was happening with the shutdown and the subsequent reopening. So this was, we had data for 10 Denver area counties, and we took a page from a tutorial on the streetlight website on how to do VMT analysis, dividing entry and exit gates. And we didn't do it for every single exit roadway in all these counties, so we just did it for the interstates. So that's what the circles are. We basically defined each point of entry from the interstates into this 10-county area as an entry and an exit. And we looked at origin destinations between anywhere in the counties and kind of ending at these gates, or origins at these gates from traffic coming through and going anywhere in the county. So we're able to kind of further restrict VMT to focus just on the travel within the counties, even if it was passing through. So if it was passing through from, on a long trip, or if it was starting out of the county and coming in, we could still account for their VMT from the streetlight. The streetlight data, I mean, all location-based data, it's not on every vehicle, obviously, it's on a fraction of them. And so, there is a method for scaling that Streetlight has for scaling up to full VMT based on correlations with loop counters. That's sort of the special sauce, I guess, in terms of how to come up with VMT. And we were able to, in some other cases with other vendors, we were able to kind of come up with our own approach for that. But it's Streetlight's put a lot of effort into how to scale it up to total VMT, and so that was something that was kind of a revelation for this project, is that now we can start looking at total VMT with telematics where we couldn't before. And in light of that, we actually looked at this analysis for VMT in the Denver area, and we compared to the 2017 VMT. And so when we accounted for, most of the trips, they started and ended in the area. Some started in the area and left the area. Some started outside the area and came in the area. And then some just completely passed through. And it's kind of interesting to see the distribution here. We also looked at this for IM, like looking at inspection areas, like the amount of travel coming from non-inspection areas into the inspection area, which is a novel application of this too. And what we found is that the Streetlight VMT estimate was about 34% higher than the data that had been submitted for the 2017 NEI. And I don't know the exact method that was used for the NEI, but again, it's likely either loop counter based estimates or maybe some travel model estimates, but at any rate, it's much lower than what Streetlight was saying. So a 34% increase in VMT for the Denver area based on our analysis, is obviously a very significant, would lead to a very significant impact on emissions. And so I think it should give the air quality community pause to think about, I mean, if we're basing VMT on loop counters, there's a lot of roads and a lot of travel that is not captured by the loop counters. The loop counters are also trying to scale up to total VMT. And so they're just scaling in a different way. They're taking all the traffic on limited number of roads and scaling it up, whereas telematics is taking less traffic on most of the roads and scaling it up, and coming to a very different conclusion. So I think this was, I'm dwelling on this because I think this was really eye-opening for me in terms of what telematics might do in terms of changing the emission inventories that we're working with. I mentioned the COVID shutdown. Streetlight was posting data every 15 days, and so we were able to look at, based on the average in 2016 through 2019 of March through May, the drops after the immediate shutdown over a year ago now in March, varied by county, and then the gradual creeping up. Of course, it would be interesting, and I'm sure there's analyses out there to kind of see what happened for the whole rest of the year. But this is what we had through the point of publishing the paper, and so it's sort of interesting to see the big drop, and then and we'd like to see some correlation to air quality, what was actually happening with air quality as a result of this. I think it's going to lead to a lot of fascinating studies. So just wrapping up, the capabilities and limitations. The telematics data, especially location data with the sample size, is a sea change in terms of the size, the geographic coverage, the temporal coverage. It can give us estimates of spatial distribution of vehicle trip activity. It can also drill down to specific hotspot locations. We were able to do an analysis, as I mentioned, looking at the Denver Broncos game and looking at travel by 15-minute increments at the highways and roads and parking lots right around the stadium. So that was great for thinking about new sources for hotspot emissions. And it can help us look at significant events, obviously a pandemic or severe weather or construction, to drill down much better. Telematics firms, including Streetlight, have developed web-based front-end applications to provide lower cost access for more aggregate but still very useful data for what we're doing. In terms of limitations, so I mentioned that the engine data seems to be drying up. We just weren't really able to find, for passenger vehicles, we weren't really able to find a source even at the level that EPA was analyzing 5 years ago. That would sort of, we could sort of pull data from, it's not saying it's not out there, but just based on what we were able to, we were hoping for a lot more in terms of, we wanted to compare OBD codes to Colorado's I&M program. There's all sorts of analysis we wanted to do, but we just couldn't because we couldn't find the data. And then that location-based data is great in terms of the sample size and the spatial and temporal distribution, but because as emission modelers, we care a lot about the vehicle, the specific vehicle class, the specific model year, the specific fuel, and the specific age, then we can't get that from location data, or we're limited in terms of information. So I think like going to the wish list, the idea of, is there a way to, and maybe even it's supplemental surveys to try to get some more information on the vehicle and some more information on the age, so that we can start to overlay activity with those things that are most important for emissions. The data samples are, I consider them passive because we're not designing an instrumented vehicle program. We're not able to stratify by age. We're not able to stratify by technology. So we're just sort of taking the huge amount of data we can get and then having to make sense of it in terms of how representative it is. And also, we really, working with the front end platform, the Streetlight Insight platform specifically, was really extremely helpful for doing the analysis we wanted to do. But there was still, we still had to consider kind of shoehorn it into the Moose model. I think Laura and I have talked. It'd be wonderful over time if Streetlight could think about a front end platform that could directly populate the Moose model or something like that in terms of the vehicle activity. And that kind of leads to the wish list item. But this was a wish list that we had, and this is my last slide. This is a wish list. We surveyed the EPA and California emission modelers, and the thing that came up first was representativeness. Ideally, a telematics data set would be representative in terms of, or at least be able to be stratified, so it could be scaled up in terms of geographic variation, vehicle class, vehicle age, technology. Able to represent inactive vehicles, because inactive vehicles produce a lot of evaporative emissions. And so we need to be able to track them as well. And the thing is, some of these things can be done with current location data. Some of these things can't. Some of these things would require engine data. So this is kind of a mix of just sort of the whole area of telematics. I think some of these are in progress and some aren't able to be accomplished. But for example, the ability to distinguish different vocations of vehicles, like rideshare versus personal, I know that Streetlight's working on that. Different truck vocations, especially with all the delivery these days and Amazon trucks, being able to track those separately would be really important for last mile considerations and impacts on emissions. EVs versus conventional vehicles, because EV charging and siting is something that we could think about. I think there's been some studies on that with telematics. Being able to identify when a vehicle's on a road grade. Mileage accrual rates, again, was something that we were able to do for CARB on heavy duty, but I think more generally for light duty as well. And there is a desire for detailed trip level data, which, again, that's location data by its nature is limited in that. And so, that would require more of an engine level type parameter. But overall, I think before I end and open it up, I just want to say, I really appreciate Streetlight's willingness to work with this and be creative and help us think about how to feed the models. And I think we've been really encouraged, certainly through the CRC projects, in terms of what we've been able to do, like the speed distributions by county. That was a huge, huge step. And now this question of VMT, and that was a new area we were able to tackle with this most recent project. And I think there's still a lot of questions on telematics, but the size of the sample and kind of the way everything is moving with that, I think we're all going to have to wrap our heads around, how to make the best use for emissions. So with that, I'll turn it over for questions and answers. I see that there's a few hands raised and questions, but Laura, Tally, do you want to moderate this?
Thank you so much, John. I really appreciate it. And I definitely encourage everyone to read the full reports. So I see a few questions. Please send me more. I've answered a few of the logistical ones. Yes, we will send out video and slides to everyone who signed up tomorrow. So John, the first question for you is, you had a slide in the beginning that showed emissions from by vehicle year, and you had a year called 1991. Does that mean 1991 and all prior years?
Yeah, that's a really good point. I forgot to mention that. So yeah, the model, the MOOS model goes back 30 years. And so 91 is everything lumped in, 91 in all prior years. And I was even a little surprised how high that was, that there's still so many old vehicles running around. I mean, that was a national estimate, or national numbers from the MOOS model. And so, there are a lot of vehicles, depending on the region of the country, that might be a different profile. Obviously there's a lot of older vehicles running around in non-rust areas. But yes, that includes vehicles from the 80s and 70s and whatever's out there. That's why there was that spike up.
Great. All right, next question. Do you have any ideas as to why there are major increases to NOx emissions using MOOS 3 compared to MOOS 2014B?
I'm going to direct you to the EPA MOOS website on that. So EPA, whenever EPA puts out a new model, they explain that very question. They show comparisons of previous model to the current model, and they explain what's different. So I'm not going to hazard an answer here. I'm just going to direct you to the EPA site on that.
All right. Our next question is, you showed the VMT comparison in the most recent paper for Denver overall. Did you do a specific comparison on the trucking groups, like heavy duty trucks, and was there a disparity there as well?
Yeah, we only focused on passenger vehicles. That was kind of the scope of the project. So no, we have not looked at that for trucks.
Okay, great. All right, another question. Our air quality and greenhouse gas analysis and modeling typically relies on speeds on an hourly basis. And we know that starting and stopping of congestion conditions can have a variety of speeds within 1 hour. And of course, the emissions are particularly sensitive at very low and very high speeds. Is there any research showing the impact of this speed variation, like smoothing within the hour at a more detailed level, especially on arterials?
That's a good question. I mean, I think there's a lot of research showing the impact of smoothing on emissions in general. So then I think the question of whether you could do it within the hour really depends on, is there data available within the hour? As part of our case study that I mentioned, we were able to look at data at 15-minute increments. There might be more of a question for Laura in terms of, how low can we go in terms of resolution of the data? Because I think the relationship is clear. I mean, if you smooth speeds, you reduce emissions. It's just, the ability to show that within an hour depends on having the activity data within an hour.
Yes, so we can definitely do it at 15 minutes. But again, I think some of these start stops are sub 15 minutes. So I also wonder if you want like a separate data set that's like, gives like an overall correction factor per speed bin for like the sub 15 minute. Or if what you're also doing is comparing time trends or comparing one city to another or one city to itself last year, it sort of evens out because the assumption, you make the same smoothing everywhere. But I think 15 minutes, if we made an emissions specific metric, which you mentioned, John, we're very interested in doing if the market demand is there. Then because this is a very emission specific need, we could look at shorter durations, shorter times at shorter speeds, right? So the answer is yes, it is technically feasible. What John did was to take metrics that we already create for our traditional planning applications and apply them to emissions, which I think already created a really big uptick in granularity, but it is possible to go further if this is something that lots of people want. Okay, more questions. Can telematics help with the catalyst function of older vehicles to understand their NOx NH3 splits? So I don't think big data can help with that, but do you think any of the OBD devices can help understand that?
Yeah, that's so the slide I showed where I showed the vehicles the malfunction indicator light on for months and months and months, and then people get it fixed, and then it gets inspected, and then it breaks again. So the malfunction indicator light is the diagnostic system on a vehicle called Onboard Diagnostics, OBD. And starting in the 1996 model year, I believe. I mean, it varies on the specific vehicle, and there's some variations between California and federal, but generally, 96 model year and later, cars are supposed to turn on a light when the catalyst goes below a certain threshold. And if you had, if you had a data logger that would collect OBD codes, yes, it would tell you that. But it would have to be, so it'd have to be like the data logger, for example, the HEM data logger I showed, that if it could gather data on OBD codes, then it would plug into the vehicle, it would drive around, and it would have to be on for a long time to kind of capture trends in MIL, but it is possible.
Cool. All right, so we have several versions of the same question, which is, okay, so we saw that the big data, in this case, streetlight data approach, created a very different estimate for total VMT in Denver than the NEI approach, but how do we know which one is more correct?
Yeah, that's a really good question. I think, I mean, first of all, I mean, sort of my first question is when we had that result, and actually I even asked Laura right before the call, was, so Streetlight, their total scale up is based on correlating where there are loop counters to the vehicles that are traveling over those loop counters. So if I'm understanding it correctly, Laura, so the Streetlight data correlates well in terms of your algorithm to the loop counters. So what we're really seeing is kind of a scale up of where there aren't counters, I guess.
Yeah.
And so, it's almost like there would need to be, I mean, if you were really wanted to study that question, I think we'd have to look at multiple, my question was, does it show up in other areas? Like, have we, if we did this analysis in other cities, would we see the same thing? Are there ways to sort of segregate it a little more to sort of make sure we're comparing apples to apples? So I mean, from an emissions perspective, I tend to think of, one way to validate very large scale inventories is to look at CO2 emissions and compare it to fuel consumption for fuel sales, for example. I mean, that's not quite apples to oranges because you always have fuel that's purchased outside the area and, burned in a different area. But I mean, there are sort of ways to ground truth big picture emissions stuff. But I mean, I would say it's, I think our study just raised the question, and I think there are more questions to resolve in terms of, is this difference real? Does it replicate in other areas? Is it pointing out a limitation of the loop counters? I mean, that we might think it is. I'm not sure, but Laura, you go ahead.
Sure. So I think, like you said, yeah, it's not just correlation, like our normalized root mean square error and our MAPE and all the comparisons to every permanent loop counter we can do, we score very well. So I think like the philosophical argument for the big data being more accurate is that it is like having a loop counter on every road segment in the county. Also, we have done validation studies compared to VMT estimated from fuel consumption, which are published by FHWA. So those are all available on our website too. But there is no great ground truth data on total VMT, right? So you're always comparing to loop counters, permanent loop counters, which are a good source of ground truth, gasoline sales, which are an okay source of ground truth, but like no one will ever really know the perfect ground truth. Like we could know the ground truth of total vehicles that cross over a loop if you leave that loop there 365 days a year. So we know the theoretical reasons the big data is more accurate because of more complete sampling, more complete coverage, and the ability to scale up with better statistical normalization methods. And all that is available on our website. All right, let's do one more question. Actually, there's two more interesting questions that I can answer quickly. So there's a question of, can this help us understand the mix of HD versus MD versus LD vehicles in a particular location? So I can answer that absolutely, and we definitely have clients who want to understand that mix, not for air quality purposes, but for other planning purposes. So that's a great, I think, like classic application of this type of data. Another question is, why, if we have GPS coordinates, then why can't we derive grade? Because that was on the wish list, grade. I think the answer is one could with a good topo map, and that exists. you see any reason why it couldn't, John?
Yeah, I mean, if you're able to sort of overlay like a tiger line or like something that has grade in it, then that wouldn't need the telematics. But I think, I mean, maybe the request coming from the agency was, can you just can tell, like, is the resolution good enough with altitude, for example, that you can just on the fly know whether a vehicle is on a grade or not, And so yeah, I think certainly kind of going back and overlaying, although I'm not sure how widely, I mean, I mentioned Tiger Line, but I know there's been a lot of researchers that have tried to sort of overlay road grade on different roads, and I'm not sure. I mean, you just sort of deal with the issue that grade data might be very coarse, it might just sort of show the grade of a large over a long period of stretch, but it doesn't show sort of really specific ups and downs. So maybe the question is, can telematics help improve what you might be able to do from just a topo map? And I think that would require altitude being at a highly resolved enough level.
Yeah, we've seen altitude metrics come in from some of our data suppliers, but frankly, it's not very good. So like, I think you can definitely know when people are going up giant mountains versus, but like it wouldn't be granular graded. Maybe be like, there's 4 classes. You're really going up, kind of going up, or pretty flat. All right. Last question, is Streetlight communicating with the vehicle for any information, or is it communicating for the vehicle at all? So there's different types of suppliers of telematics data. So in John's study, he worked with some devices that do have a connection to the onboard computer. Streetlight's data in this study was not connected in any way to the onboard computer. It's connected to like mobile devices like phones. We have other data streams, and we're pursuing other data streams that are connected. So maybe you could start to get this on off. But as John was saying, the availability of data from the telematics computing connected world has really diminished in the last 5 years, whereas the availability of data from the connected phone world has increased. However, we will be adding and announcing very shortly some additional truck connected vehicle data feed. So we're working hard to get more back into the big data landscape as that trucking world sort of recalibrates around some of the new privacy laws. All right. We have a few more questions that we're not going to have time to get to, but I'm going to write them all down, and we know who asked them, and we will try to email you a response. In the meantime, thank you so much for your attention. This has been really great and really thoughtful conversation from all the questioners. And as I said, we'll be sending out this information soon, so please share it widely. We're really excited to start working on air quality emission inventories as a sort of new and expanding use case with big data. So thank you so much.
Thanks, everyone. Thanks, Laura.